So we're going through these different parent functions, and we're applying the exact same transformations to them. And we are on x cubed, the cubic function. So we copied and pasted all this yesterday. Let's go ahead and write the equation first that's specific for this function. What does it mean to be inside the cubic function? Yeah, inside before you cube it. Would you say underneath the exponent? I like that. So we're going to have a 1/2 and then blob cubed plus 3. So the 1/2 and then plus 3 on the outside, and on the inside is going to be your -4 parentheses x minus 1/2. Okay. So the parent function here is x cubed, and I'll go ahead and draw that one in yellow because that's your reference graph. And you wouldn't need to sketch this necessarily because you could visualize it. We don't need the f there? No. F is the placeholder for a particular function, right? What I have written up here, what I copy and pasted, this is just any function. This could be x cubed, square root of x. If our function f is actually x cubed, we're replacing f with x cubed. Okay, so I guess we can show that here. F of that is now this cube. So we're actually applying the specific function. All right, so let's see if we can do this one now without doing the sequence of transformations, and we'll pick purple for our final answer here. What is the 1/2 going to do to the graph of x cubed? What would be the explanation again? Vertical compression by a factor of 2. If you say by a factor of, it has to be greater than 1. So if it's not, just flip it. That's just going to make this graph a little bit squattier, right? If you compressed it, it's going to be a little bit squattier. Okay, we don't have to show that. It'll basically have the same shape. The negative in front of the 4 is going to reflect it across the what? Y-axis. That's going to be pretty impressive, right? Because now it's going to be decreasing from left to right, coming from quadrant 2 through the origin and into quadrant 4, right? So just hold that picture in your head. It's going to be decreasing like this. The 4 in front of the x does what? Horizontal or vertical? Horizontal, stretch or compress? Compress by a factor of 4. So that's going to take that graph and compress it towards the x-axis. That's going to have the effect of making it steeper, right? When you compress it horizontally, it makes it steeper. Again, we're not going to really show that. So my final shape is just something that looks similar to this, maybe a little steeper, that is decreasing now from quadrant 2 into quadrant 4. I pick it up and move it right 1/2 and up 3. Now the point to follow on the cubic function is also the origin. That's what we're going to call the inflection point later on. So that's -1/2 and this is 3. So if I just put that dot right there, now I know my final shape looks something like this, and then it's going to look like that. I'm sorry? Oh, yeah. I moved it the wrong way. Very good. We're moving it right 1/2. We could fix that pretty easily right here. Call that 1/2. And now if I pick this up, we'll just move it over. Nope, I can't do that. Don't wait for me. You're probably already done. You're on the next one. Something like that. Thank you. There you go. So there's your final graph. The thing that I told you I'll remind you all about is the y-intercept. I'm not going to make you find the x-intercept yet, but you want to make sure it crosses in the right location, either in positive y-land or negative y-land. Is there any doubt that it's crossing the y-axis in positive y-land? No. Now, if you wanted to make sure, you could go ahead and find it. To find the y-intercept, which in general I'll make you find anyway, the simplified exact value. To find the y-intercept, you plug in a 04x. So let's go ahead and plug in a 0 into this line right here. You're going to get 0 minus -1/2, which is -1/2. -1/2 times -4 is positive 2. 2 cubed is 8. Half of 8 is 4. 4 plus 3 is 7. So the y-intercept is 0, 7. Okay, there you go. What's the domain of this graph? All real numbers. And what's the range? We get the range from the graph. It's also all real numbers. Good. All right, the next one, the natural log of x. These are your two new ones right here, right? The last one's ln and e of x. So when we have a quiz on Monday, you think I'm going to give you like the x squared or the x cubed? or even x, the familiar ones? No, it'll probably be one of these. In fact, it will be one of these. So we warmed up yesterday with the natural log of x, so we have a little bit of experience with this one. Let's go ahead and write the equations first, specifically for this new function. The 1/2 is on the outside. We're replacing f with the natural log of and plus 3. And then to be on the inside of the log means to be the thing you're taking the log of, which of course I called that the what yesterday? The argument. Good. So this is the argument. All right, we'll do this one also in one fell swoop. The x and y axis. In yellow, I will sketch the parent function, which of course looks like that and has an x-intercept of 1, 0. So the natural log of 1 is 0. Same thing. The 1/2 is going to compress it vertically by a factor of 2. That's going to make the graph a little bit shorter, you could say, vertically. The negative in front of the 4 will reflect it across the y-axis. And again, that's a significant one because now the graph lives to the left of the vertical asymptote, yeah? And it's decreasing. So it's going to come in right here from the left and live to the left of the vertical asymptote. The 4 is going to be a horizontal what still? Compression. That's going to make it a little bit steeper. But that's it for the shape. So our final shape is coming in from the left, approaching the vertical asymptote at 0. Now I pick it up and move it right 1/2 and up 3. And whenever you have an asymptote, you need to show the new location of the asymptote. The only type of transformation that's going to change the vertical asymptote is what? Horizontal shift. The only thing that's going to eventually move a horizontal asymptote, is a vertical shift. So if it used to be at 0, now it's over here at 1/2. So I'm going to label that as 1/2. I'll put my dotted line there. And you don't have to follow around the x-intercept. There's really no point on the natural log graph that you have to follow around, because following the x-intercept around is going to be difficult. So, again, all you have to do is draw it coming in with the right shape, something like that. But there's one thing that I'm going to hold you to, right? Is it crossing the y-axis in the right place, either in positive land or negative land? The way I drew it, I have it crossing in positive land. But as we saw yesterday, it could also maybe be down here. Now, even though we moved it up 3, maybe that's an indication that it does cross some positive land. But I want to make sure I have it in the right spot. So what are we going to find to make sure? The y-intercept. So get used to finding the y-intercept. And like we saw in the warm-up yesterday, if it's something that we need a calculator to get the decimal value of, we could still probably determine if it's positive or negative without the calculator. So show me h of 0. And once again, if I plug in a 0 in for x up here, 0 minus 1/2 is negative 1/2. Negative 1/2 times negative 4 is positive 2. So I end up with 1/2 times the natural log of 2 plus 3. Now, I don't know what the natural log of 2 is, do you? That's one that you might come to learn later on. It's about 0.693. But if you didn't know that, you could still determine if that's a positive or a negative number, right? Because the natural log of 2 on the parent function, remember, it crosses at 1, 0. So if you're taking the natural log of anything bigger than 1, it's going to be what type of number? Positive. And if you take the natural log of anything between 0 and 1, it's going to be negative. So the natural log of 2 is just a positive number. A positive number times 1/2 is still a positive number, right? And then a positive number plus 3 is a positive number. So that's still a positive number, which means our graph actually crosses the y-axis somewhere in positive land. So can I leave my blue graph like that? Yeah. Had it come out to be a negative number, then I would just draw it somewhere down there where it crosses in negative land. So the y-intercept, that's the last thing that you want to find just to kind of make your graph a little bit more accurate. And of course, once we have that, we can find the domain now. What's the domain of this function? Negative infinity 1/2. Brackets or parentheses? Parentheses. And the range? All real numbers, all day long, right? Monotonic? Yes. Yeah, monotonic decreasing, good, over its domain. Okay, and then the last one here, e to the x, first thing is to make the equation. And we're replacing f with e. What does it mean to be inside the e function? In the exponent, good. So in the exponent, which you got to write it a little bit smaller, and you got to make sure you keep it elevated. You don't want it falling out of the exponent. Oops. There it is. So our parent function has what? A horizontal or a vertical asymptote? Remember, E looks like that. And if you extend that E, horizontal. And it's monotonic increasing, passes through the point, 0, 1. So e to the x and the ln of x again are what? Inverses of each other. So the x-intercept of the natural log was 1, 0. It's now the y-intercept of e to the x, 0, 1. The vertical asymptote at x equals 0 is now the horizontal asymptote at y equals 0. All right, very quickly again, we're going to compress it vertically by a factor of 2. The graph is going to be a little bit flatter. We're going to reflect it across the y-axis. Again, a very significant one, right? Because now instead of an increasing function, it's going to be a decreasing function. But it hasn't changed the horizontal asymptote yet. If we compress it horizontally by a factor of 4, that just makes it a little bit steeper again. We don't have to show that. So our final shape is going to be some decreasing function. Some decreasing function. But it still lives above the horizontal asymptote, yes? All right. Pick it up, move it right 1/2. We don't have to follow this point around. And then move it up 3. Which of those two is more significant, the right 1/2 or the up 3? The up 3, because that's going to move the, what? Horizontal asymptote. If it was at y equals 0, now it's up here at y equals 3. And remember, you always draw that first. No. No. The y-intercept without any compression would be up at 4, but remember, we've already changed that. When we compressed it by a factor of 2, the y-intercept went from 1 to 1/2. You're not going to have to follow the old y-intercept around, because you know what we're going to do in the end? We're going to just find the new y-intercept. And right now, you don't have to find x-intercepts. So if the old horizontal asymptote was at y equals 0, you add 3, now it's at 3. And it's going to be what? Increasing or decreasing? Decreasing. Above or below the asymptote? Above. So that's as accurate as you need to be. So for your log function, and well, all the functions essentially that have asymptotes, those become your critical characteristics that you want to make sure you know where they go. And you draw those first. Now there is no doubt that we're crossing the y-axis in positive land, yeah? Because it's above 3. Let's go ahead and find it anyway, though. H of 0. If you plug in a 0 for x, you're going to get -1/2 times -4, which is 2. So you're left with 1/2 e squared plus 3. You're going to leave it like that. Now, e squared is approximately what? E is about what? Yeah, if e is about 2.718 or 3-ish, right, then e squared is going to be 3-ish squared-ish, which would be 9-ish, a little less than 9-ish, right? So half of 9-ish is 4.5-ish. 4.5-ish plus 3-ish is 7.5-ish. Does that look like it's 7.5-ish? Nod your head, yes. And by the way, look at my purple graph. Does it look like it's horizontally compressed vertically compressed by a factor of 2 and horizontally compressed by a factor of 4? Nod your head. Yes. Yes. That's the same criteria I'm going to use on yours. Say, yeah, looking good. Looking good. As long as it has the right shape, I'm not going to test whether or not it's the right steepness. How will I test you on the steepness? I'll make you write a written verbal explanation, right? Vertical compression by a factor of 2, horizontal compression by a factor of 4. That's how I know you understand, but we won't show it on the graph. Does that answer your question?
No.
Shoot.
I was just going to ask, like, so I'm using to figure out if it's positive or negative, as long as it's like, square root to a positive number or whatever, then it should be positive land.
Right. You're going to be able to tell. I'm going to create the equation so that without a calculator, you'll be able to tell if it's going to be a positive or a negative number. If it's not something that you can find on your own, okay? Same thing over here. But you do have to know something about the graph in order to figure it out, right? Like we knew the natural log of 2 was a positive number because it's bigger than 1. All right, so that was a nice activity because we got all the parent functions involved, but we did the same thing to each of them. And it doesn't matter the graph you're starting with. Once you have a change in an equation, it'll manifest itself the exact same way on any and every graph that you're starting with, okay? So let's go ahead and fill in the blanks here. This is on the standard transformation form. We always interpret a dilation, which is a generic term for stretch or compress. It's like a vector. We have to say whether it stretches or compressions. Does it get bigger? Does it get smaller? By a factor of some number. And we can abbreviate by a factor of as BFO. I'll let you do that. But remember, whenever you say by a factor of, it always must be greater than 1, because you're telling me which direction we're going by a factor of what number greater than 1. If you say a dilation of a half, that's fine. But a dilation of a half would be either a vertical compression by a factor of 2 or a horizontal stretch by a factor of 2. All right, so let's go ahead and say it. The absolute value of A. Now, why do I say the absolute value of A? A could be what? Negative. So if I just look at the magnitude of A, thank you, that's going to be your vertical dilation factor. And if its magnitude is greater than 1, that's going to be a what? Vertical stretch or compression? Yeah, let's just call it 3 halves. We'll use 3 halves. And x, we use x squared as an example. We'll use 3 halves. 3 halves is greater than 1, right? So that's going to be a vertical stretch by a factor of, you would say 3 halves. Or in this case, in general, by a factor of, let's just say by a factor of the absolute value of A. So what we're saying there is the graph is 1.5 times taller in our example. If the absolute value of A is between 0 and 1, like here's an example, y equals 2/3 x squared, that's going to be a vertical what? Compression. I'm going to abbreviate that comp by a factor of what? Would you say by a factor of 2/3 if that's our example? By a factor of 3 halves. How'd you get 3 halves from 2/3? Reciprocate it. So it would be by a factor of 1 over the absolute value of A. If your A is less than 1, just reciprocate it. So for us, our 2/3 would say it's a vertical compression by a factor of 3 halves. It's 1.5 times shorter. You're telling me the direction and by how much. And of course, if A is less than 0, if it happens to be a negative number, that's going to be a reflection across the what axis? X-axis. That's an X-axis reflection. And I guess I should put the example in front if I want to be consistent. That would be like y equals negative x squared. And y'all are pretty familiar with negative x squared, right? It just opens down. So the vertical dilations are exactly as what you would expect them to do. If it's bigger than 1, it's going to make the graph taller. If it's less than 1, it's going to make it shorter. The horizontal dilation, that happens on the inside. That's the absolute value of B. Your example would be if it were, let's call it, if it's greater than 1, that would be 3 halves x before we square it. It's on the inside now. What is that going to do? It's a horizontal stretch or compression. Compression, the opposite of what you'd expect. It's not 1.5 times wider. That's what 3 halves is. It's 1.5 times narrower. So it's a horizontal compression by a factor of what? Would you say 3 halves, right? Or in this case, by a factor of the absolute value of B. If it's already greater than 1, then that's your dilation factor. But if B is between 0 and 1, like on the inside if we had a 2/3 x before we squared it, that's going to be a horizontal stretch by a factor of not B, but the reciprocal of B. So in our example, if you see 2/3 x, it's not 2/3 as wide, it's 1.5 times wider, or 3 halves times wider. And if B is less than 0, that's going to be something like this. If it's negative, it's going to be a y-axis reflection. Maybe this is a bad example because we saw that yesterday. If you reflect the graph of x squared across the y-axis, are you going to see any change? No, because it's already what type of function? Even. So maybe negative x cubed would be a better example. All right, so that takes care of the dilations. Y'all, I think y'all are used to that because I think in Algebra 2 now they're emphasizing the correct way to say stretch and compress, because some of the old textbooks didn't do a good job. They would say, like right here, this is a horizontal stretch by a factor of 2/3. If you stretch something by a factor of 2/3, you're actually making it what? You're making it smaller. Okay, so I think now the new books are corrected. All right, if C is greater than 0, these are your shifts. If C is greater than 0, here's your example. It would be like x minus 5 squared. Remember, the standard form is x minus c. So the c value is what follows the minus sign only. So in this case, c would be 5. That's going to move the graph what? Right c. We'll just put right c units. And again, it's the opposite of what it appears. Because there's a minus there, minus 5 might look like it's negative 5 to the left, but it's to the right. And if c is less than 0, then it's going to look like this. It'll look like something like x plus 5, because that's really x minus negative 5. So it's really the negative 5 there. That's our c value. And that moves it to the left c unit. So you know how to do that. Now back outside on the vertical, this is going to be exactly as you would expect. If d is greater than 0, like x squared plus 5, that's just up d units, because it's like the last thing you do. You have your y value in hand, and oh, you want me to add 5 to it? Okay, now it's 5 times big, or 5 units larger. And if d were less than 0, like x squared minus 5, then that's going to be down d units. Down d units. Yes. Down d units. That would be also what you would tell your dog if guest came over and it jumped up on him and its name was d units, right? Down d units, down. Yeah. Anyone have a dog named d units? All right. Here we go. We're going to do exactly what we did up here with example 4. But instead of like using the same transformations for a bunch of functions, we're just going to look at one graph at a time, and they're each going to be unique. Okay? So here we go. F of x. Our goal is to sketch it. Step 1, identify the parent function. What's the parent function? The reciprocal function, 1 over x. Step 2, put it into standard transformation form. Is it in standard transformation form? No. Now I'm going to put the optional step here that Weston, you asked yesterday if it's required. The answer is no. But we're going to have it as a times 1 over b times x minus c, close, plus d. For the reciprocal function, that would be the standard transformation form. To be inside the reciprocal function means to be in the denominator. So any number that's in the numerator, you kick out front and you call it an a value. All right, ready? Here we go. Our function then is the negative 3 that's in the top. I'm going to kick it out front. I don't like it. That leaves a 1 in the top, yes? Now, remember, there's 2 things to do in the denominator, or the inside in general. Put the x term first and then factor out the coefficient. I'm going to do it in 2 steps. The minus 1 at the back is your d. That looks good. Now, if you walked away at this point, which so many students do, you're going to get everything correct but your horizontal shift, which means you're going to get it wrong. Talk to me. Yeah, go ahead. What must we do in the denominator? Factor out the coefficient of x. That's your b value. But in order to get the horizontal shift right, you must factor it out from the c value. Or it's not really the c value yet. Now this one's easy, right? What do you get when you factor a 2 out of a 2? A 1, because you're dividing. There you go. That's standard transformation form. Now let's talk about what these things do, because I'll have you explain this. Let's just go ahead and list it. We're not going to list them every time, but on the first one we can. What does the negative out front do? X-axis. So x-axis reflection, followed by, what does the 3 do? Good. A vertical stretch by a factor of 3, followed by the 2 in the denominator would be a horizontal. It's multiplied with the x, so it's horizontal stretch or compression. Again, think on the inside, it's opposite. It's not 2 times x. It's not twice as wide. It's half as wide. So we're compressing it by a factor of what? 2. Good. That's going to affect the shape, and then all we're going to do is pick it up and move it left one, and then down one. Anyone have a dog named One? No? Okay. Now I'm gonna try and just go straight to the final graph. Do y'all need to see what the parent function looks like in there? Yeah, it would be helpful. I'm going to draw it in yellow, just because it doesn't show up, but we can at least refer to it. Remember, the parent function looks like that. This is the one that has vertical and horizontal asymptotes. Now remember, the stretches and compressions themselves, you don't ever have to show that. So you really don't even have to worry about the magnitude of A and B for the graph, right? The magnitude of A and B. Stretch, compress, you don't have to show that on your graph. I will expect you to write the explanation. But if A and B are negative, those are reflections, and that changes the orientation, and you have to be very aware of that. So this negative in front reflects it across the x-axis, which means now this branch in quadrant 1 is now going to be down here in quadrant 4, and this little branch down here in quadrant 3 is up here in quadrant 2. So now it's still in vertical quadrants, but it's 2 and 4 instead of 1 and 3. So remember, it's in 2 and 4, 2 and 4, 2 and 4, 4 and 2, 2 and 4. Got it. Now, when we pick it up and move it, that's pretty significant, because when I pick it up and move it left 1, that's going to change the location of the what? The vertical asymptote. Which flavor should we use for the final graph? Red. Okay. Not red? Yeah, not today. Not red. Yeah, blue. There we go. Any day today, but not today. All right. So -1, that's your new vertical asymptote. We'll draw it first. And then down 1, that's going to move the what? Horizontal asymptote. So there's -1. There's my new, you can call it your new x-axis if you want to, because it kind of is. So the intersection of the vertical and horizontal asymptote, which used to be at the y-axis and x-axis respectively, now can become your new x and y-axis. And remember, it lived in quadrants 2 and 4. So let's go ahead and draw it in there. Come from one asymptote, depart from it smoothly and gradually, and head to the other one. And down here, we'll just draw it like that. Looks good. Now, is there any doubt that we're crossing the y-axis in negative land based upon the asymptotes? No. For sure we're crossing in negative land. Let's go ahead and just verify it. We'll always verify with the y-intercept. F of 0, that's all you need to show me. When you say F of 0, you're telling me, hey, I'm taking x equals 0, I'm plugging it into the function for f, I'm finding my y-intercept. Now, you can plug it into any one of these versions. It's probably easier to plug into the original one, believe it or not. If you plug in a 0 for x into the original one, the 2x becomes 0, and you get -3/2 minus 1. -3/2 minus 1, which that's something that we can simplify, right? What is that? 1. -5/2, or you can call it what? 3/2 is 1.5, so -1.5 minus another dollar is -2.5. If it's a terminating decimal, I don't care if you use decimals, but I'll use fractions most of the time. Is that reasonable based upon my graph? Yeah, totally. How did I do that? I plugged it in 0 for x. I always. Oh, 1 is how many halves? If I have this one as the denominator 2, I'm just in my mind multiplying by 1 by 2 over 2, right? So I got -3/2 minus 2/2. -3 minus 2 is -5/2. Okay. What's the domain of this function? -infinity to -1. Union -1 to infinity. Yeah. Or you could say set of all x such that x ain't -1, right? That works also. Now, can we verify that algebraically? Sure we can, right? Because remember, we did this already. We have a denominator. 2 plus 2x shall not equal 0. So 2x shall not equal -2. X cannot equal -1. Man, isn't it nice when the algebraic domain matches up with the graphical domain? Yeah, that's nice. That's a pretty good indication that we are awesome and correct. Yeah. Now the range we get from the graph, and now we can find the range with confidence because we found the range, the domain, and verified it. What's the range? Yeah, same thing. Set of all y such that y is not -1. Or interval notation if you prefer that. Is this function monotonic? Yes. This function is monotonic what? Increasing over its domain, which we've already stated, so you can say that. For all values of x not equal to 1, it's monotonic increasing. Does it have any local max or min? Local max, local mins? No hills or valleys? No. I could ask for anything. Anything that we study regarding a function, I could ask. What would be the limit as x approaches -1 from the right-hand side? Louder, right? Negative infinity, right? Confidently, because as we're approaching -1 from the right, here we go. Where are we going? We're going down, 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 down. What would be the limit as from the other side? The limit as x approaches -1 from the left-hand side. Positive infinity, yeah. What would be the limit as we approach -1? The general limit. dne, good. If it were going up on both sides, we could say infinity. If it were going down on both sides, we could say negative infinity. But the general limit has to be dne because it's one of each. Excellent.
What determines whether or not a line crosses the horizontal line?
There's a lot that goes into that. If it's a periodic function or a sinusoidal function later on, there's a good chance it might. You can actually determine whether it does later on using calculus. And here's how we know that. The ones you see right now are not going to cross their horizontal asymptote. But in general, if a function did cross it in the short run, it would have to turn around and come back down. And if it did, we would be able to find a local maximum there somewhere. And that's how we would know that it would cross. But right now, we don't have the tools to investigate that. So the ones that you see are not going to cross their horizontal asymptotes. Great question. All right, any other comments about 5A? Y'all want 5B, I can see it. Let's do 5B. Parent functions, what? What's parent function? Yeah, the exponential, right? E to the x. Were you going to say the natural base exponential?
I don't know what I was going to say.
The parent function is e to the x. Okay, everyone got that in their head? You see it in your head? Maybe we'll draw it later. All right, we need to put it into standard transformation form. Do I need to write out the template in terms of e to the x, or can we do it without that now? We're trying to get the training wheels off the bike, right? The 3 in the front, where should he go? Is he an A, B, C, or D value? He's not an A value. He's a term, right? So he's a D value, right? It's +3 minus. So just because it's in the front doesn't mean it's an A. He's going to be a +3 at the back. Dividing by 5 is the same as multiplying by what? 1/5. And there's a negative out there. So -1/5 is now going to be your A value times e to the. Well, notice it's already got my x term first. So all I have to do now in my exponent, instead of rewriting the terms first, is factor out a what from both terms? 4. So in the exponent, 4 parentheses x plus. When you factor a 4 out of a 7, you get what? 7/4. That easy. What you started with divided by what you factored out. 7 divided by 4, I will call it 7/4. Because it doesn't go in evenly. Perfect. Now, if we're gonna write the explanations, which I'm just going to talk about them from left to right. Again, that's the beauty of standard transformation form. You can list what's happening from left to right. The negative in front is a reflection across the x-axis. Good. The 1/5 is going to be a vertical compression by a factor of 5. Good. The 4 is going to be a horizontal compression by a factor of 4. And then we got our final shape. We pick it up and move it left 7/4 and up 3. Got it. Good. Now, of the 4 and the 1/5, the only one we need to show on the graph is really the negative, right? The negative, because that's going to be a reflection across the what again? I forgot. X-axis. Okay. So in Lelo, let's draw our parent function. E to the x has what type of asymptote? I forget a lot. Thank you. Horizontal. And remember, it's monotonic increasing, so it looks like this. Passing through 0, 1. Again, the stretch and compressions you don't need to show, but the reflections you do. That one's going to reflect across the x-axis, right? First. which means now the graph is going to live where in relation to its horizontal asymptote? Below. And it's going to be increasing or decreasing? Decreasing. It's going to come in here from below and go down like that. I got it. That's my final shape. Now, when I move it left 7/4, is that really something that we want to show or need to show? No, because the horizontal asymptote's not going to be affected, right? It goes east to west forever. And this y-intercept, I don't really care moving it. But the +3, that's significant because what does that do? After we reflected it, we reflect it first and then move it up 3. So my new horizontal asymptote is going to be at 3, which I'm just going to call right there. I know it's not the scale, but I'm going to give myself some room. And you said it lives above or below that? Below. Okay, so it's decreasing below. Now, before you walk away from the graph, notice I have it crossing the y-axis in positive land. It could be that it was shifted enough to the left, because we did shift it left, right? That if I shift it left enough, it's going to cross in negative land. So you can just slide it left to right. Does it cross at 0? Does it cross the y-axis in negative land, or is it in positive land? We better do what?
Add or subtract 7/4 from the coordinate 0, 1, and
No, because we compressed it. Remember, we compressed it first by a factor of 5. So the 1 went now to a 1/5. You could do something like that, but it's very hard to follow around the old y-intercept. It's probably best just to find the new y-intercept, right? How do we find the new y-intercept? Plug in a 0. And how do we communicate to people that we're plugging in a 0 for x into the function g? G of 0. Man, that function notation is something else. Now, we have two different versions of the function into which we may plug. Which one do you want to plug in? The easier one. The bottom one, I like the top one, really. But you plug it into the bottom one. I'm going to plug it in the top one. We should get the same answer. Yeah. So if I plug into the top one here, 4 times 0 is 0. So I get e to the 7th. And that's about all I can get, right? I can get 3 minus e to the 7th over 5. And all I got to know is if that's a positive or a negative number. Well, e is about what? 3-ish, right? 3 to the 7th is going to be big or small? Pretty big. Divided by 5? Still pretty big. Do you think it's going to be bigger than 3 or smaller than 3? Should be bigger than 3, right? Even when you divide it by 5. So 3 minus a number bigger than 3 should be negative. Right, this is going to be a negative number. Oh, goodness. Is my graph correct? No. And luckily with Notability, all you got to do is lasso it and slide it over to the left enough until it crosses in negative line. If you were drawing it on paper, you would probably want to erase it or find the y-intercept first, maybe, right? So you only have to draw it once. So what we did there is by shifting it left 7/4, we shifted it left enough that it did cross in negative land. Any local max or mins? No. Any symmetry? No. Monotonic? Monotonic, decreasing. Good. What's the domain of G? All real numbers. Do you think it'll ever be not all real numbers for the domain of an exponential? No, it'll always be all real numbers. And what do you think about the range of a log function? Do you think the range of a log function will ever not be all real numbers? No. The log function will always have a range of all real numbers, and the exponential function will always have a domain of all real numbers because they're what's of each other? Inverses, yeah. Now, the range of the exponential we get from the graph, what's the range? Negative infinity up to 3, bracket or parenthesis? Parenthesis. We don't quite reach the horizontal asymptote. Good. Any questions on B? We got time for one more. Letter C is, what's the function's name? Well, the parent function is the log, but the function's name is u of x. U, not me, u of x. I would either one of these two, B or C. They make great quiz questions for Monday. All right, let's see if we can get through this one pretty quickly. The parent function is the natural log of x. Is it in standard transformation form? No. The pi in the front, is that a? No. It goes in the back with the E. Okay, and they team up to become team D. So plus pi plus E. That's just a number. I'm going to group them together. They're not like terms. But if pi is about 3 and E is about 3, then 3 plus 3 is about what? 6. So they're about a 6-ish, somewhere in the 6-ish vicinity. That's good enough to know. And is that going to be up, down, left, or right 6-ish? Up 6-ish. Great, good to know. On the inside, is the inside ready to go? Is it perfect? No. Step 1. I'm going to call that negative 5, 6x. If you have the x in the numerator, you can kick it out of the numerator off to the side. And now you have a coefficient times x. That works. But it's still negative. And then I have a plus 5. What's my a value? There is something. It's implied to be a 1. Okay, so you don't have to worry about it. Am I good to go? Is that standard transformation form? No. What's my b value? Negative 5, 6. But is my c value 5 or negative 5? No. Again, don't walk away yet, because on the inside, at this level, you will have to factor out something to get it into standard transformation form. Now let's do the easy part first. When I factor a negative number out of a positive number, I'm going to be left with a negative number. Okay, that's good. Now, when I factor a 5, 6 out of a 5, what am I left with? 6/5. Again, this is where it gets a little bit more fun. Here's how you can do it. Off to the side. You're starting with a 5, right? And you're dividing out a 5, 6. Or you can put negative there if you want. You're dividing out a 5, 6. Now I got 5 divided by 5, 6. I can do state change flip, right? Dividing by 5, 6 is the same as multiplying by 6/5. Well, what happens with your 5s? They divide out, leaving you 6. There you go. Now, quickly to redistribute and see if it works. Negative 5, 6 times negative 6. Negative times negative is positive. What happens with your 6s? They divide out, leaving 5. If you can basically just look at it, that's fine. But in general, what you're starting with, off to the side, divided by what you're factoring out, simplify off to the side, drop it in there, mentally redistribute to make sure it's correct. Okay, and notice I have double sets of parentheses there, don't I, in the argument. The outer set contains the argument. This inner set contains the horizontal shift. Let's go straight to the graph. This will be fun. This will be the last thing we do. This will take us into the weekend. What a great way to go. All right, in yellow, let's do lime green this time. It doesn't show up that much either, but it's different. Is this the parent function? Yes, or is that the wrong one? I get them confused. I forget a lot. Is that right? I'm right. Thank you. Remember, the L in the natural log looks kind of like a vertical line, like a vertical asymptote. It always has to go through 1, 0. Yeah. But we're not going to necessarily follow that point around, the 1, 0. The important thing for us is where is the vertical asymptote, and on which side of the vertical asymptote does it live, and is it increasing or decreasing? That's what's important to us. What does the 1 in front do? What does the 1 in front do of the natural log? Vertically stretches by a factor of 1. Do we have to do that? Do we have to say that? No. Okay. The negative in front of the 5, 6 is a reflection across the y-axis. Kind of important? Yeah, very important, because now the graph lives to the left of the vertical asymptote, and it's what? Going down. It's decreasing. Good. So keep that in mind. The 5, 6, this is a great one. I'd have you write it out. The 5, 6 is going to be a horizontal stretch. Good. By a factor of 6/5. Good. And you can leave it like that. It's also 1.2. It's 1.2 times wider. It's less than 1, so it's not going to be compressed because it's on the inside. It's going to be stretched by a factor of, and then you flip it. Good. And that's going to give us our final shape. Good to know. It's still going to be decreasing to the left of the vertical asymptote. We pick it up and move it right 6, which is important because that's going to change the old vertical asymptote. And then we're going to move it up 6-ish, right? Which, yeah, who cares about that? All right, so let's go straight to the final graph. In pink, I'm going to call this 6 right here. Right? The vertical asymptote was at 0. We moved it to the right. Everything, so now it's at 6. And we're going to draw it now just decreasing, coming in from the left. Uh-oh. I have it crossing in positive y land. Once again, Depending on the shift, it could cross a negative or positive. So before I walk away, I better find the y-intercept. So u of 0. And I'm going to plug it back into the original just because it's easier. When I plug in a 0 for x here, I get 5 minus 0, which is 5. So I get the natural log of 5 plus pi plus e. Any doubt as to what the sign of that number is? It's going to be positive. The natural log of 5 is positive because it's bigger than 1. So if that's greater than 0, is that my graph? Can it work? Perfect. I'm crossing in positive y land. Awesome. Well, we'll finish up D, E, and F on Monday after the quiz. Your quiz will be either e to the x or natural log of x transformed. So make sure you know how to do those. Have a great weekend. I'll be here Monday at 7 if you have questions.